Specialist Maths. I'll be your host, James Mott, and today, in today's instalment, we'll be looking at differential calculus. In particular, we'll be looking at how to use the CAS to calculate and evaluate a second derivative. From there, we'll be looking at points of inflections and reviewing them. In particular, what are they, how to find them, and also the relationship between the function, its derivative, and the second derivative. And then build upon a vocabulary and review the ideas of concavity and review what it means to be concave up and concave down. And throughout today's lesson, we'll also be looking at some exam-style questions that we'll see for second derivatives, points of inflections, and concavity. So, for the second derivative, we may be familiar with two different types of notation, d squared y over dx squared, or f double dash. Now, on CAS, the second derivative is given by more of an operator notation, so d squared over dx applied to f of x. So a typical exam question could be, we're given a function such as 3 arc cos x over 2, and we want to try and find the second derivative at x equal to 1. So what we can do, if we're trying to evaluate a derivative, we can head over to our menu and go to our calculus menu. And our second option here is derivative at a point. So in this particular option here, our variable is x. Our value, well, we want to evaluate it at x equal to 1. Now, to easily transition between the boxes, we can press tab on our CAS. Now, at the moment, the current option is the first derivative. We can change this to being the second derivative. And that way we can evaluate the second derivative straight away with ease. Okay. Now from here, we can just simply type in the function that's given to us. And remember, for arc cos, another way we can write that is inverse cos. So to get our inverse cos, we can head over to our trig button on the left-hand side of our CAS. In the submenu, there's inverse cos just below cos. And we have x over 2. And there's our second derivative at x equal to 1. So that's a really quick way of evaluating derivatives and a really time-efficient way for exams. Another exam question that could be thrown our way is one where we need to determine which of the following equations or statements are true. So in this example here, we're given y is equal to sine 4x minus 1, and we need to figure out which one of these particular equations are true. So what we can do is on a calculator page, we can define the equation given to us. Now, normally we define things as fx, but in this instance here, we're not using this function to sub in or differentiate. So what we're actually going to do, or what I'm going to do, is actually define it as y. So we can define it through menu, actions define. So y is equal to sine of 4x minus 1. Okay. And what we're going to do is actually just literally type in the equation given to us in each option. And hopefully when we type it in, if that is indeed a valid rule, the output should return true. If it's not, we'll just get something as an output. So this first option here, y minus 16 times the second derivative, we can type that in. So y minus 16 times. Now, to efficiently type in the second derivative, on the right-hand side of our CAS, next to the book button, there's this little button here that has a couple of templates. So if we click that, we should get this little submenu pop up. And the tile that's highlighted there, D2 over some D and some squares, that's the second derivative template. So it's a really quick way of obtaining the template for the second derivative. So we can click enter and then type in x and y, and we want this to be equal to 0. Now note that at the moment y is in bold. That's because we've just defined it above here. So pressing enter, we're getting some garbage as an output. So what we can do, we know that that's not true. So we can go ahead and try the next option, y plus 16. Now rather than have to type everything out once again, all we're doing is simply changing the negative to a positive with a coefficient of 16. So what we can do is press up to highlight our previous work, and we want to use that. So once it's highlighted, we can press enter to bring it to the next line, and then go ahead and change negative to a plus. We hit enter once again, and we see we're still not getting true. So we can go ahead and try each option. Let's try option E, because I think that one might be a winner. So we can type in 16 times y plus 4 times the derivative. So again, we want to type in the derivative. We can head over to our template button next to the book button that we just used. And next to the second derivative is our first derivative template. So we can type in dy dx there. Plus, and the second derivative, once again, using the template button, second derivative, and we want this thing to be equal to 16 times cos 4 times x minus 1. And there we get the result as true. So what that's telling us is that this equation holds up for this particular value of y. So this is indeed a true statement, and therefore our answer in this case would be E. So that's a really neat way and efficient way of tackling these sort of functional equations, which we might also see in methods. But for Spesh, if we see these guys, we can use the template button to efficiently get our derivative and second derivative. We need to use it. Okay, points of inflection. So over the course of term 1, we may have seen different ways of how we can obtain the second derivative. So a really quick way we may have seen is just to let the second derivative equal to 0. Now that's not quite enough to find points of inflections, because we also need the concavity to change. Or that is, we want the sign of the second derivative to change as well. So let's actually see this in action. So at the moment, we've got this nice looking cubic. Now, on the top right of the screen here is the graph of our derivative. Nice looking quadratic. And down below is the graph of the second derivative, which is a linear. Okay? So as we sort of vary our points, we can see as we're heading towards the maximum here, the turning point, our derivative is 0 over here. Right? Then as we're sort of heading towards this sort of pink dashed line here, we're going to pick up the second derivative equal to 0, which corresponds to the minimum of our gradient function, and that happens to be a point of inflection there. Okay, and we can continue on and see that at the minimum, once again, our derivative is 0, so it's going to be a turning point there, and our second derivative is actually positive there, so it's going to be a local minimum. Right. So we can actually, as a really quick way of finding points of inflections, we can just figure out when the second derivative is equal to 0, but that's not quite enough. It doesn't always work out. So in this sort of polynomial here, right, once again, we can track what's happening as we move towards that point of inflection given by the pink line. So at the moment, as we go over the maximum there, right, the derivative is equal to 0. And as we're heading towards the point of inflection, bang, the second derivative is equal to 0. Right? We've got a minimum on our gradient function. But then what's interesting, as we keep on moving along our curve, we notice that our second derivative is 0 at another point as well, right there. So at this point here, the second derivative is also 0. Our gradient is 0. But what's interesting is that on our original graph, our function, we're getting a turning point. So it's not just enough to say that the second derivative is equal to 0. What we really need is to actually see the change in sign of the second derivative. Right? So what we can say is that at this point here, at the second derivative, so at the point of inflection, sorry, as we cross it, our second derivative is changing from a negative to a positive, whereas in the second instance, where the second derivative is 0, right there, the sign doesn't change. We're still at a positive second derivative either side of that 0, right? So what we need to be mindful of is, yes, we can find out when the second derivative is 0, but just like in methods, just like in Spesh, a great technique is to always look at our graph. Never underestimate the value of looking at a graph, okay? So that's a very sort of, I guess, basic way of trying to explain when and where points of inflections occur. Now we're going to build up that sort of vocabulary a little bit by looking at the idea of concavity. So concavity is just a very formal way of describing this. when we change our sign of our second derivative. So just like before, same cubic. Highlighted here in orange is a section where our second derivative is actually negative, as we can see here in red down the bottom. And what we say is that this part of the graph is concave down, where the second derivative is negative. Right? So as we sort of vary our points, we can see that our second derivative is always negative along here. What's also interesting is that for our gradient at this section here, or this part of the graph here, it's actually a decreasing function. And also a nice little beauty to finish off with is that the tangent anywhere along this section of the graph is always above our curve, which is a neat little fact. And then as we cross the second derivative, so as we cross the point of inflection, we get our second derivative equal to 0. And then all of a sudden, as we keep on moving along, our graph becomes concave up. And then we also note that the second derivative is also positive from there on out. And our gradient becomes an increasing function. And finally, the tangent is now below our curve always. So what we're really saying here is that, yes, we want the sign of the second derivative to change for points of inflection, but also, more formally, we want our graph to change from concave up to concave down, or vice versa. And that's also true of this one, this trickier question from before. So in this part of the graph, where the graph has a negative second derivative in red and in orange, right, anywhere along here, that second derivative is negative. As we pass the point of inflection, we're going to change from a negative second derivative to a positive second derivative, as we see there. Whoops, come on. There we go. And then as we move along, that second derivative is always positive. And even when we touch 0, for our second derivative at the minimum, right, with 0, but either side, we're still getting a positive second derivative. And also, more importantly, for our gradient function, for this part of the graph here, it's always an increasing function. So the function there is increasing. So those are sort of the relationships we want to try and develop, and also the vocabulary for points of inflections and concavity. So the main takeaway here really is that points of inflections occur when the concavity changes from concave up to concave down and vice versa. All right, so if we had, say, an exam question which wanted us to sort of determine where the function was concave down, typically this would be sort of a multi-choice question. What we can do is first of all define our function. Now, if we're comfortable using the define feature via the menu actions define, that's okay. But another shortcut we could use is the assign command. So what we do in sort of instance, we can type in fx, and for assign, where that template button was before next to the book, we see in blue there's a little colon equals. So press Control template button to get this assign symbol here. And we're going to type in our function, making sure we multiply our factors here. Oops. X minus 1 squared times x plus 1. Okay. Now, for concave down, if we can't quite remember, from our visual beforehand, we saw that concave down, the condition is when the second derivative is less than 0. So what we can do is we can solve for when the second derivative is less than 0. So menu, algebra 1 for solve. Remember, to get our second derivative really quickly, we can hit that template button to get our second derivative template, and then type in fx, and then making sure we get outside of that bracket. Now we want this guy to be less than 0, and we want to solve that for x. And then these values are where the graph is concave down. All right. Now another sort of question we could be thrown in an exam, typically in exam 2, is we might give them some sort of function at the start of the exam, and typically we want to find out features of this graph, of this function. We want to find the stationary points, and then from there, any points of inflections, and we also might be asked to sketch this function. Right? So because we're doing quite a few operations with it, we're going to define this function. And just like before, for efficiency, we're going to use the assign command. So Control template to get this little blue symbol here. And we're going to say that's 2 times x over 4 plus 3 times x power 5. Alrighty, stationary points now. So to get our stationary points, we require our derivative equal to 0. But what we're actually going to do here to get the output looking nice, we're actually going to use simultaneous equations. And I'll explain why. So in algebra, number 7, system of equations. 2 equations, x and y, sounds good to me. Here we go. So, like always, we're going to try and solve the derivative equal to 0. So, using our template button, we can get the derivative straight away. So, the derivative of our function equal to 0. Right, we'd normally do this, get some x values, and then sub them back into our function to get our y values. A neat little trick on CAS to do that efficiently is to say y is equal to f of x. Because if we think about this by hand, we're going to solve this equation, as I said, equal to 0, get some x values, plug them into our function f to pick up our y values. And in doing so, we get our output really, really neatly, although at the moment these guys aren't looking too pretty. And also, I haven't answered the question correctly because the question asked me to correct the 2 decimal places. So by default, the CAS will give it in exact values. But if I want it in 2 decimal places, I can highlight my work, bring it down, and then press Control-Enter to give an approximated answer. Okay? And from there, we're getting the x and y values straight away as 0.80 and 0.23 correct to 2 decimal places. Okay? So that's all the idea of using simultaneous equations. Now, just for completeness, I'll do it in one line. Is a neat little way of just doing the calculation efficiently on CAS. All right. Now for points and inflections. We're going to do the exact same thing, except we're going to let the second derivative equal to 0. So like before, at the moment, my template's pretty good. All I need to do is change my derivative to my second derivative. So I can highlight, press Enter. Then I can delete my derivative and then put in my template for the second derivative. There we go. fx. Because as we saw before, we want to find out when the second derivative is equal to 0. And then with those x values, we're going to sub them in to find y. And finally, just before that, we want correct decimal places. So we're going to press Control-Enter to get it in some decimals. Now, we've got 2 answers here, the origin and some other points. Now, it's not enough just to leave it here. All right, we need to be careful and smart and determine if these things are actually points and inflections, because like we saw before on our graph, way back here, all right, sometimes when the second derivative is 0, we get a point of inflection, but sometimes we may not get a point of inflection. We might get a local minimum or a local maximum. All right? So what we need to do is do our due diligence and actually look at our graph. Right? So we're going to insert a graphs page. So we can go Doc, Insert Graph. Right? Now we've already defined our function fx. So we can type it in, whoops, and sketch it. Right? There it is. Looks a bit wacky. Now I'm just going to change the window settings just so I can have a better clear view of what's going on here. So in menu, we can change our window settings by window zoom. And I'm going to change it to make it -3, 3. And remember, to efficiently and easily get between all these boxes, we can press Tab each time. So -3 and 3, and that's okay. That's a little bit better. Now, what we're going to do to check where these points and inflections are, we're going to sketch the second derivative as well. So pressing Tab gets us back to our graphing template, and we're going to type in the second derivative. So from our template button, second derivative of fx. Right, that's in blue, that's in red. So we can see from our graph here that the second derivative is 0 at the origin, and there's another point here that we picked up before from our calculator page. However, at the origin, we can clearly see that either side, the second derivative is negative. Whereas at the other point of 1.15, the second derivative crosses the x-axis and changes from negative to positive. So what this is telling us that in actual fact, that the only point of inflection is this one here, at the 1.15, whereas the origin is not a point of inflection because the second derivative, the concavity, isn't changing. Second derivative is still negative on either side of that 0. Okay? So what we can actually say as a final answer is that only this coordinate is the point of inflection for our graph. So when x is equal to 1.15 and when y is equal to 0.23, correct to 2 decimal places. Now that's a nice algebraic way of doing it. A graphical way, if we are going to be another way of efficiency, is I'm just going to hide our second derivative for now. And what we can do is use the analyze features in our graphing page. So in menu, we've got analyze graph, and in there, thankfully, we've got a point of inflection command that picks up any points of inflections. So what we can do, because down the bottom here it says lower bound, we would want to try and click to the left of where we suspect there's a point of inflection. Right? We're going to hover over, and as we can see, we're not picking up any points there. So that's yet another way that's indicating to us that at the origin, there's no point of inflection. No good. Let's try that 1.15 now. So once again, menu, analyze graph. There we go. So we can sort of, again, click to the left of where we think it is, hover over, and bang, there we go. 1.15 and 0.23. Okay. So that's yet another efficient way. If we just wanted the point of inflection, maybe it's a 1-mark question, that's a really efficient way of finding the point of inflection, correct to 2 decimal places. Whereas if we needed a little bit more work, we might have to actually figure out what the second derivative is equal to 0, and then sub it in to get our y values. And I'll also say what's important, another sort of important point as well, is that if we use this analyze graph feature, at the moment, it is rounding it to 2 decimal places. If you want some more decimal places, the calculator option will give you more. Otherwise, you may have to change your settings in the graphing menu through settings here and change it to a float, perhaps 4 or 5, pick up some more decimal places from there. Okay, so that's if a question would ask for correct to 3 decimal places or 4 decimal places, that's how we can modify that quick graphical way. Okay, hopefully you found this useful too, and that's all that we have for today with points of inflections and concavity. We do sincerely wish you the best of luck and stay safe. Thank you for joining us today.